Our universe is a place of awe-inspiring wonders. From the smallest particles to the largest galaxies, the cosmos is filled with mysteries that captivate our imagination. But perhaps one of the most perplexing questions facing modern physics is the curious case of the missing antimatter. The story begins with the Big Bang, the event that brought our universe into existence. In those first fleeting moments, the universe was a chaotic soup of energy, constantly transforming into particles of matter and antimatter. This creation process, according to our current understanding, should have produced equal amounts of both. It's like flipping a coin. You'd expect an equal number of heads and tails over many tosses. However, when we look out at the universe today, we find something astonishing. The universe we observe is overwhelmingly composed of matter. Galaxies, stars, planets, even we ourselves are all made of matter. Antimatter, on the other hand, is incredibly rare, only observed in fleeting cosmic events or created in laboratories. This imbalance, this cosmic preference for matter, is a puzzle of epic proportions. To grasp the depth of this mystery, we need to understand what antimatter actually is. Imagine the universe as a mirror. Matter, the stuff that makes up our everyday world, has a mirror image, antimatter. For every particle of matter, there exists an antiparticle with the same mass but opposite charge. Take the electron, for example, a negatively charged particle that orbits the nucleus of an atom. Its antimatter counterpart is the positron. The positron has the same mass as an electron but carries a positive charge. When matter and antimatter meet, they annihilate each other in a burst of pure energy. This mutual destruction is one of the most efficient energy-releasing processes known to physics. This symmetry between matter and antimatter makes the imbalance we observe even more baffling. If the Big Bang truly created equal amounts of both, where did all the antimatter go? Why is our universe dominated by matter, while its mirror image seems to have vanished? The dominance of matter over antimatter is not just an academic curiosity. It has profound implications for our very existence. If the universe had equal amounts of matter and antimatter, they would have annihilated each other long ago, leaving behind a universe filled with radiation but devoid of stars, planets, and life. The fact that we are here to ponder this cosmic riddle means that something must have tipped the scales in favor of matter during the universe's infancy. Some unknown process, some fundamental asymmetry in the laws of physics, must have favored the production of matter over antimatter. This asymmetry, even if incredibly tiny, could have resulted in a slight surplus of matter over antimatter in the early universe. As the universe cooled and expanded, this surplus of matter, the matter that makes up everything we see today, would have been left over after the majority of matter and antimatter annihilated each other. Scientists have proposed several theories to explain this matter-antimatter asymmetry, each more intriguing than the last. Some theories suggest that the laws of physics are not perfectly symmetrical. Perhaps there are subtle differences in the behavior of matter and antimatter that we haven't yet detected. Others propose the existence of new particles and forces beyond our current understanding that could have played a role in tipping the balance. Some even hypothesize that there might be regions of the universe, as yet unobserved, where antimatter dominates. The search for the missing antimatter has become a major quest in modern physics. Experiments at particle accelerators like the Large Hadron Collider are recreating the conditions of the early universe to study the properties of antimatter with unprecedented precision. Scientists are also searching for signs of antimatter in cosmic rays and distant galaxies. The mystery of the missing antimatter is a testament to the boundless wonders of our universe. It is a puzzle that continues to challenge our understanding of the fundamental laws of nature. The solution, when we find it, promises